Now let's basically derive the key concepts of angular theory. And this short video will be essentially putting together the relationship between the angular and translational parts. So it's pretty important to understand how we get the results we do. So we're going to consider an accelerating wheel and wonder if the points on the wheel all have the same angular acceleration and linear acceleration. Those are questions we'll address. So here's our wheel, and we'll consider a point on the wheel. With respect to x, it's at angle theta and position r, the vector r. And it has some speed. It's going around the circle, so this thing is rotating counterclockwise around a circle. But what we're going to do is increase the speed of this object, so we have an angular acceleration. And the distance it's gone is s, and we know s is equal to r theta. So we're going to take the rate at which this whole system changes. In other words, ds dt is r, which is a constant, d theta dt. There it is. And ds dt. What is ds dt? Well, it's just the rate of change of the arc length. And the rate of change of the arc length is just the speed. That's all it is. So that's the linear speed, the rate at which this arc length changes. All right. And then r d theta dt is the rate of change of angular position, which is angular velocity. So the parallel or the tangential speed of the particle is r omega. So regardless of any acceleration at this point, the speed at this given moment is r times omega. And it kind of makes sense that it's related through r, because if we're going around the circle, say I'm going around in 1 second here with a small r, there's a certain speed, but if we increase r and go around in a second, obviously the speed has to increase a lot because the distance to go around the circle in the same amount of time has greatly increased. So r omega is v. Now let's consider acceleration. So we have an alpha, angular acceleration. Well, if there's an angular acceleration, then whether it's a solid wheel or whatever it is, it's considered a wheel. And a point on the wheel is then accelerating in the direction it's moving if the rate at which it's rotating is increasing. So there's a tangential acceleration. Now, we learned that the tangential acceleration in such a thing is the rate at which the speed changes. So it's the derivative of the magnitude of the velocity, or the speed. But we know that the speed is r omega, so it's just r d omega dt. R being a constant in this case. So that's the tangential acceleration, which is r alpha. So in the same way that velocity is related to omega through r, the tangential acceleration is related to the angular acceleration through r, proportional to r in both cases. Hopefully that makes sense. So now we have a radial acceleration as well. Don't confuse angular acceleration with radial acceleration. Very different. Radial acceleration is just what we know it to be, v squared over r. But now we know v. V is r omega, so it's r squared omega squared over r, which gives us the simple result, omega squared r. So omega squared r is something we use a lot in rotational problems. The radial acceleration is omega squared r. So it looks kind of funny all by itself. How did radial acceleration become omega squared r? Well, now we see where it comes from. So we'll be using that. And so there it is. We're going to hook it off the end here and add the vectors, the tangential acceleration and the radial acceleration, to give us a resultant vector acceleration that we're going to call the linear acceleration, for lack of a better term. And since we know the two parts, namely the tangential acceleration, the radial acceleration, we can get the linear acceleration by taking the square root of the sum of the squares. It's that big animal there. R factors out, and we see that we have an expression for the total acceleration of an object accelerating in a circle. both components of which are related to the radius r. So, is there angular acceleration? Yes, there is. The reason there is because alpha is equal to d omega dt, and the rate at which the angular velocity changes is a constant. Well, that may or may not be, but whatever it is, it's the same at every radius. At any given point on the circle, the rate at which that angular velocity changes is the same thing. Is the acceleration constant? No, the acceleration is not constant, because no matter how you look at it, whether it's the tangential part, it's proportional to r. If it's the radial part, it's proportional to r. So definitely not the same linear acceleration. Let's do an example problem that includes an airplane where the prop is spinning at 2400 RPM. Well, the forward airspeed is 168 miles an hour, which is about 75 meters per second. The tip of the propeller must not exceed 270 meters per second, or about 80% the speed of sound. So the combined effect of all the motion is such that the tip can't exceed this 270 meters per second. And of course, to answer the question, you don't want to break the sound barrier because that violates local ordinances about sound levels, because you have shock waves that can be disturbing to people, even though I think it's pretty awesome to experience little sonic booms. But everybody's unique in that way, I guess. Well, the VPA, the velocity of the plane with respect to air, that's 75 meters per second. So that's a separate motion from the spin of the prop, but the combined effect must not exceed 270. So let's do a vector diagram. VPA is the translational part. And then we have another vector. The velocity of the tip is the result of the rotation. And the rotational part of the tip velocity is r omega. So when we combine them together, we get the total velocity of the tip. V total is really the total tip velocity. That's what can exceed 270. So let's solve. Pythagorean theorem, Vt squared, total squared, VPA squared plus Vtip squared. And we know that the tip rotational speed is r omega, so that's r squared omega squared. So now what we need to do is figure out, well, what's omega? Let's calculate omega, so then we can solve for the radius, the minimum radius, or maximum radius, I should say, so that we don't violate the 0.8 times the speed of sound limitation. So omega, we have 2400 revolutions per minute multiplied by 2 pi radians per revolution. So that gives us radians per minute, but we want radians per second, so let's divide that by 60. That gives us 251 radians per second. Now we can solve for r squared, just using this, Vt squared minus VPA squared over omega squared. And let's go ahead and plug the numbers in. We know the total can't exceed 270, so 270 minus 75 squared, both of them, over 251 squared gives us the maximum radius being 1.03 meters. Very good. And so now what's the acceleration of the tip? Well, the vector acceleration of the tip really is only the radial part, because there is no acceleration from the translation. So it's just radial, which is omega squared r. 251 squared times 1.03 gives us a radial acceleration of 65,000 meters per second squared. So you don't want to be hanging on to the tip of that prop. And actually, if you think about that, that's 6,500 Gs. So you can imagine that the material from which a prop is made has to be very resilient, because it has to withstand forces that correspond to, thousands of Gs. So you have to very carefully construct these airplane props. And indeed, they are not cheap. Trust me, I have an airplane prop, and I'm constantly babying it and fine-tuning it and polishing it and putting little guards on the tips so that rocks don't chip it on my little plane. You don't want to have to replace those very often. Okay, so that's an introduction to angular theory.